So one thing that we might ask ourselves is how we implement the buffer that we need for the prior example. So let's redraw our operational amplifier. Okay, so we'll add our compensation capacitor, and what we would do is add a common drain stage that ties into our buffer, but flowing in the opposite direction of our normal signal path. And we'd have to bias this with some extra transistor that pulled some more current through it. We'll call this transistor M8. Of course, all of our other transistors are typically labeled M1, M2, M3, M4, M5, M6, and M7 here. So we add this buffer M8, and we have to bias it with a transistor M9 pulling current through it. And the problem that we find with this solution is that it costs too much power. I'm probably going to have to, in order to make 1/GM for M8 small enough, push a fair amount of current through M9, and that current is coming from a voltage supply VDD, which means that the power is too much. And so a better solution, rather than using a buffer, is to add a nulling resistor. And what we're going to do with this nulling resistor is simply place a resistor in series with our compensation capacitor. So looking at our simple model that we've been looking at over the past, of our input stage being represented by a GM, an output resistance, and a capacitance, and our second stage being represented by the same. A GM, a resistance, and a capacitance. And of course, our output being taken off of that capacitance and potentially having a load capacitance tied to it. What we're going to do for compensation is we're going to add our compensation capacitor, CC, but we're going to put a resistor in series with it. And we're going to call this resistor RZ. And what we're going to do is move this 0 due to this compensation capacitance where we want it. So if we did KCL at the input node and the output node, we would find that there were a couple of poles and zeros. Our first pole would be omega P1 is equal to 1/GM2 times R1 times R2 times CC, exactly as it was before. We'd find omega P2 was approximately equal to GM2 over CC, CL, the load capacitance, which is approximately exactly the same as it was before. We could find a third pole, omega P3, that's approximately equal to 1 over RZ times C1. And this pole is due to this nulling resistor, as we're calling it. And finally, we'd find our zero frequency, omega Z1, is equal to 1 over our compensation capacitance times 1 over GM2 minus RZ. And so what we find here is that we can move this zero from the right half plane to the left half plane simply by controlling the size of the nulling resistance RZ. If RZ is less than 1 over GM2, then our pole remains in the right half plane. But if we make RZ bigger than 1 over GM2, our zero moves into the left half plane. So we can relocate the zero here by changing the size of the nulling resistance. And we'll look at what our strategy for doing so is in the next part of the lesson.